This is the first formal lecture for the course PH4113, Symmetries in Physics. In this and subsequent few lectures, I'm going to lay down the basic mathematical theory that will be important for this course, which is of course group theory. We will not cover all of group theory. We'll just cover those parts which will be most useful for physical applications. Even that in itself is a huge topic, so we are going to sort of pick and choose the topics that we will discuss, but most of the useful techniques that we will need to apply group theory to physics will be studied in the next few lectures. And then of course we are going to go on and talk about applications of these techniques to actual physical problems. Now, the reason why group theory is so important in physics is symmetry. Symmetries have always been a very, very important central part of physics. In fact, not only does it help in simplifying a lot of calculations which we physicists do as a routine, it actually goes so far as to even restrict the possibilities that are available. That is, what theories can be written down, what cannot be written down, these are dictated by symmetry principles. So, well, it is rather understandable that group theory will play a central role in physics. However, despite its immense importance, group theory did not really catch on as a staple of mainstream physics until the advent of quantum mechanics. In fact, it was only after quantum mechanics became a rather mature subject that its applications or the utility of group theory in quantum mechanics became apparent to physicists. Even that is not quite true, because the person who introduced group theoretical methods to quantum mechanics, Eugene Wigner, faced a lot of oppositions from many stalwarts. Well, for example, Pauli, or maybe it was Schrödinger, who exactly came up with this term is not so clear now after the years, came up with this term, Gruppenpecht, which essentially described the feeling that many stalwart physicists had towards this new technique which mathematicians had built and which was now invading this space. They thought of groups basically as some kind of irritating pest rather than as a useful tool. In fact, Wigner recalls quite clearly that when he described some rather nice calculations that he could do using group theory in quantum mechanics, Schrödinger had responded that, okay, these are very nice, but surely no one will still be doing it this way in 5 years. Now, it's not really true that everybody opposed Wigner. One of Wigner's classmates, for example, von Neumann, actually was very, very supportive. In fact, he went on to say so much as, oh, these are old fogies. In 5 years, every student will learn group theory as a matter of course. Well, the reality is somewhere in between, in the sense that today it's possible to be a student of physics without learning a lot of group theory. True. However, if you want to do any serious kind of theoretical physics, group theory is almost certainly one of the most important topics that you will have to learn. Not that this opposition to group theory was limited to the so-called grand old men of quantum mechanics, like Pauli and Schrödinger. Later generations also found it rather difficult to come to terms with this entirely new kind of mathematical concept. One very important person in this fight against the Gruppenpecht was John Clark Slater. He wrote an article in which he explained why group theory should be done away with from mathematical physics. In fact, later on, paraphrasing that article, he wrote in his autobiography that the authors of the Gruppenpecht wrote papers which were incomprehensible to those like me who had not studied group theory, in which they applied these theoretical results to the study of the many electron problem. Let me point out at this stage that John Slater was one of the leading experts in the world in the theory of many electron problems. And this is what he said about the use of group theory there. Continuing with Slater, he went on to say, the practical consequences appeared to be negligible, but everyone felt that to be in the mainstream, one had to learn about it. So it's understandable that many physicists who could actually go about their calculations perfectly well without using group theory felt a bit irritated by the fact that you had a new crop of people who were using the group theoretical language everywhere, and to their minds this was not really adding any value to their descriptions, only making it more and more incomprehensible to people like them. In fact, quite a lot of them rallied around Slater, and Slater sort of became a folk hero among a section of physicists for this famous article where it is said that he slayed the Gruppenpest. The situation has turned around from that rather remarkably, so that today we cannot even think about advanced theoretical physics without invoking group theory in a big way. Group theory indeed has become very, very central to physics. And that is why we will spend a lot of time in this semester trying to understand how to use group theory in physical problems. So let us now go on and try to describe how symmetries lead us naturally to groups. Okay, at this point, let me just point out that symmetries are not the only reasons why groups and their theory is important in physics. There are other applications of group theory to physical situations where symmetry takes a backstage, but those are comparatively rare. Most of the applications of group theory to physics stem from the fact that symmetries are best described by groups. Now, what kind of symmetries are we talking about here? Well, there could be symmetries of the laws of physics. There could also be symmetries of physical objects. Since the latter is easier to understand or sort of recognize, let me start with an example of a symmetry of a physical object, in this case an equilateral triangle. So consider this triangle, the red one on the screen right now. I've labeled the three vertices A, B and C, but let me just point out that these labels are just for our reference. The actual triangle comes with no such labeling. All the vertices are identical. Now, what exactly is a symmetry or a symmetry operation? A symmetry operation of this equilateral triangle would be something which you can do to this equilateral triangle which will not change it. Or in other words, if I just asked you to shut your eyes, did something to the triangle, and then asked you to open your eyes again, will you be able to tell that I have done something to the triangle? If you are able to tell whether I have done something to the triangle, then what I have done is not a symmetry operation. If, on the other hand, you are in no position to figure out what I have done to the triangle, or whether I have done anything to the triangle at all, then that particular operation is a symmetry. Now, one symmetry operation that is available for every physical object or geometrical object, no matter how complicated its shape might be, is the very first one in our list, is simply doing nothing to it. If you do nothing to the triangle, of course, you cannot tell whether we have done something to it because, well, it has not changed at all. So this is the identity operation, in other words, the do nothing operation, which is there in every group of symmetries or every set of symmetries of a physical object or a geometrical object. And it's usually denoted by the letter E. E, of course, stands for ein, the one in German. After all, historically, most of group theory did originate in the Germanic-speaking countries. So, it's natural that much of the symbolism is inherited from the language of Germany. Now, another way in which you could denote the same do-nothing operation is by this symbol out here. Most of you would be aware of what this symbol means. It's a standard symbol of permutation of three objects. This just says it's a permutation in which A goes to A, B goes to B, and C goes to C. All we are saying is this is what happens to the vertices of my triangle, which remember are there just for the labeling, under these symmetry operations. So A, B, C, none of them change under the identity. Of course, that's a rather uninteresting symmetry operation, although we will see that uninteresting does not make it unimportant. The identity is a central thing in the mathematical theory that's going to follow. Okay, what other symmetries are there? Well, one obvious symmetry you can think about is reflecting the triangle in a median which goes through one of the vertices. This is a vertex labeled capital A. Let's call that median small a, and we are also going to label the operation of reflection of the triangle in this median by the same letter small a. So reflection small a, what does it do? Well, what it does to the vertices is shown here inside the triangle. A of course stays A. What used to be the vertex C has come here now. So this is the vertex C now, but which has, so the original C has come to B, original B has come to C. So this is what happens under this particular symmetry operation. ABC becomes ACB. So A stays A, B goes to C, C goes to B. Well, what else can you do? You can reflect in the other medians, and of course there will be symmetries as well. So you have a reflection which we label small b, is a reflection in the median passing through the vertex capital B, and under this reflection B stays B, A changes to C, C changes to A. So A and C gets interchanged under this. And then you have the reflection C, which of course keeps C unchanged, A and B switch. A becomes B, B becomes A. Well, then we come to another different kind of symmetry operation, which is a rotation. Now, as you can see, an arbitrary rotation will leave the triangle in a configuration which is different from the original configuration, so you should be able to tell whether something has been done. However, if you rotate exactly by 2 pi by 3, which is 120 degrees, then you should not be able to tell whether a rotation has been done at all or not. Notice that under this operation, of course, the triangle stays unchanged, but all three of the vertices move from their places. What used to be A has now become B, so A goes to B, B has come to C, and what used to be C has come to A. So this is the particular permutation of the vertices which corresponds to this 120 degree rotation about an axis which passes through the center of the triangle and is normal to the plane of the triangle. Now, if this is a symmetry, and it is obviously, then doing it twice would also obviously leave this triangle unchanged. So, if I were to do a 240 degree rotation, or 4 pi by 3 rotation, it would again give you a symmetry of the triangle. And in this rotation, A goes to C, B goes to A, and C goes to B. We are labeling this particular rotation F simply because E has already been taken by the identity, which by the way is another rotation. It's a rotation through 0 degrees. So we see that the set of symmetry operations of this equilateral triangle has 3 reflections, the ones labeled A, B and C, and 3 rotations, a 0 degree rotation, a 120 degree rotation, and a 240 degree rotation. Of course, you might say, why don't we keep on doing the rotation over and over again? But it's easy to see that if you were to rotate, say, through 120 degree thrice, that would be a 360 degree rotation, which is effectively doing nothing again. So, under such a rotation, not only would the vertices not change, no points of the triangle would change. So, this finite set of 6 numbers are all the symmetries of the equilateral triangle. Let me point out, however, that we only are considering symmetries in the plane of the triangle, you may assume for concreteness that the two faces of the triangle are colored differently, so that flipping it over, a rotation through 180 degrees about any one of the medians will not be a symmetry. So we are only keeping ourselves to those symmetries which keep the thing entirely in a plane. Now, as you can see, these are 6 operations, and corresponding to each of the operations, there is a permutation of the vertices. Now, this is not an accident, as we will see later, that there is a deep connection between any group and the group of permutations. But for the time being, let's come back to these symmetries. The most important reason why we are talking about these symmetries is that the set of 6 symmetries form a group. That is to say, if I were to do any 2 of these operations, one after the other, I would get one of these operations again. Now that is sort of obvious, because if you did one symmetry operation, that would leave the triangle invariant. Do another symmetry operation, that also leaves the triangle invariant. If you do these operations one after the other, obviously the triangle will stay invariant under the joint action of both, which means that these 2 actions done one after the other should also be a symmetry. So these 6 symmetries, which we are showing here by this diagram, which essentially shows you the lines along which the 3 reflections take place, and these 2 rotations, D and F. Also there's an E, which is don't rotate at all. These are the actors in our game right now. To see what happens when you apply 2 operations one after the other, let us just start by focusing on a particular point on the triangle, not a special point, some arbitrary point. Let's say this particular point P, and let us apply 2 successive operations on this point P. Let us first try applying the operation A. This is the operation A, and I have just written this on this side just to highlight that this is what we are doing. So the point P under the operation A has moved here. So you will see this happen at 2 stages. You will see what happens to the point as you do the geometrical operation. You will also see what happens to the permutation. So after the operation A, let us do another operation. Let's say B. So when I do B on this point with A of P, you get B of A of P, which is this particular point, which is what we call the result of BA, the composite operation BA, which is first do A, then do B, acting on the point P. And of course, the corresponding permutation is out here in blue. So when you want to do one after the other, this is BA acting on P. And one way to understand what this is take a look at the permutation. This permutation takes A to C, B to B, C to A. But what we can do is we can rewrite the same permutation in this form. Instead of writing the top line as ABC, I could just write the top line in any order I want, as long as what these elements map to, that stays okay. So what I can do is rewrite the top line in the form ACB, which matches exactly this top line here, the bottom line here. And A of course goes to C, C goes to A, B goes to B. It is the same permutation as this one, it's just that it has been written slightly differently. And the reason why we have done this is that in this form it's very easy to compose the 2 permutations, that is apply one after the other. Notice what this green, the permutation in green, A, the first permutation, is telling you is that A will go to A. The second permutation will tell you that the result A goes to C. So ultimately A ends up in C. And the first permutation takes B to C. The second one takes the resulting C to A. So overall B goes to A. Similarly C goes to B and then B stays B. So overall C goes to B. So the result of these 2 operations done one after the other is this: A, B, C go to A goes to C. That is, you can just imagine that you have just omitted the two repeated lines and you've got A goes to C, B goes to A, and C goes to B, which is of course this operation down here, namely the same thing as rotating the whole thing by 240 degrees. So BA acting on P is the same as f of P, and this works for any arbitrary point you pick on the triangle, which means that the group operation BA, the symmetry operation that you get by first doing A then doing B. Notice that although when we talk about it, we are calling this BA, it's really A first, B after that. That is exactly the same as F. So the level of group operations BA is the same as F. Similarly, if after doing F, what you did was a 120 degree rotation, then you will carry the point back from here to where it originally was, that is back to P. So DF acting on P is the same as P itself, and again this works for an arbitrary point, and that means that DF is the same as the identity, do nothing. And another way of talking about this is D, the operation that we have done now, undoes the action of F, so D is F's inverse. So this essentially tells us that when you consider symmetry operations on an object, in this example we took an equilateral triangle, but you should be able to realize that this works for any physical object whatsoever. If you take the set of all symmetry operations acting on that object, and you define a multiplication within quotes of these symmetry operations by essentially saying that the product simply means do one operation after the other, you expect to have some nice mathematical structure coming out of it, and this mathematical structure is exactly what we call a group. So now let us try to recount what exactly is a group. So formally, if you were to define a group mathematically, a group is really not just a set of objects, it's a combination of two things. It's a tuple. It's a tuple whose first element is a set G and the second element is an operation which we are denoting by a star. So G comma star, that's a group. It's an ordered pair where G is a set and star, which is a map from G cross G to G, is a binary operation. Of course, binary operation, the name means that it's a map from G cross G to G. But that's not enough. This binary operation has to have certain properties. What are the properties? Well, the properties are associativity, which says that for all G1, G2, G3, pick any three elements in capital G, this result here holds. That is, when you form the product G1, G2, G3, it does not matter where you put the bracket. You can either do G2, G star, G3 first, then do G1 star that, or you can do G1 star, G2 first, and then do that star G3. Note that we are not making any statement about whether G1 star G2 and G2 star G1 are equal at this stage. And so the order in which the elements occur, we are not allowed to change that. However, how you associate these elements, whether you take G2 and G3 first and then G1, or G1 and G2 first, then G3, you should get the same result. This, of course, is a standard property which many mathematical operations have, like addition and multiplication, which is precisely the reason why even in colloquial language you can say things like add 3, 4 and 5. Subtraction, for example, is not associative, and which is why you will never hear somebody say subtract 3, 4 and 5. That's because where you put the brackets does matter when you're talking of subtraction. 3 minus open bracket 4 minus 5 close bracket is very different from open bracket 3 minus 4 close bracket minus 5. So, even your ordinary daily language usage would tell you which operations you do regularly are associative. You can talk about multiplying 3, 4 and 5, but not dividing 3, 4 and 5. So associativity is a property which group multiplication must have. That's one of the defining properties. Another property is the existence of an identity, that there exists at least one element in the group G and it will turn out that it's a unique element, there's only one such element in the group, such that for all G, small g belonging to capital G, E is composed with G. E star G must be the same as G star E, and that must be the same as G. In other words, when you compose an identity or multiply the identity either on the left or on the right by any group element, that particular group element gets returned. The identity will not change that group element. Then comes the third important property. That's the existence of an inverse. This property demands that for every element small g in capital G, there must exist an element G inverse, small g inverse, again in capital G, such that G composed with G inverse and G inverse composed with G are both equal to the identity. This means that every element can be, the action of every element can be undone, which is something which is obvious as far as symmetry is concerned. You do an operation, the object doesn't change. You undo the operation, the object doesn't change again. So the undoing must very well be a part of the set of symmetry operations. Now, those of you who have seen the definition of a group before may feel a bit uneasy at this stage because there's one very important property which I've left out, which is the property of closure, which is for all G1, G2 belonging to capital G, G1 star G2 belongs to capital G. So usually when we talk about properties of the group multiplication law, these are the properties we talk about: closure, associativity, identity, and inverse. However, there is a reason why I did not talk about closure till now, because frankly, if you say star, this operation is a binary operation, it's a map from G cross G to G, then that implies closure. The very term binary operation implies that the set G is closed under the action of star. So, if we are saying the star is a binary operation, there is really no need to add the closure demand separately. However, very often we might be talking about a subset of some bigger set, and we may not be sure whether the set is closed under what was a binary operation for the bigger set. So closure is something we will have to check in those cases. Well, associativity is a property which turns out to be pretty complicated to check whether a particular operation is associative or not, because in principle what you need to do is take all possible triplets and check whether this particular rule applies for all. However, in most of physical applications, the operations, the symmetry elements that we are going to talk about are things you do to some object, and there the product essentially means composition. You do one thing after you do another. So if G1, G2, G3 stands for three things which you can do to a set, then what does this G1 star G2 star G3, this particular thing on the left here, mean? It means that you are going to do G2 star G3 first on that object, and then you are going to do G1. Which of course now means you are going to do G3 first on that object, then you are going to do G2. That's what G2 star G3 is. And then you are going to do G1. So the upshot is G1 star within bracket G2 star G3, the thing on the left here, essentially is do G3 first, then you do G2, then you do G1. It's very easy to see that the right hand side also means exactly the same thing. Do G3 first, then you do G1 star G2, which is do G2, then do G1. So, when you are talking about actions on a set and you're talking about composition of these actions, doing one action after the other being your product rule, then associativity is automatic. So it's trivial for transformations, although it is a very difficult property to check in a general multiplication rule. It's very, very easy and trivial when you're talking about transformations. Now, usually when we write these things, we will write G1, G2 instead of G1 star G2. We will just drop the star. Although, remember the star is very much a part of the story and is in fact central to this whole thing. Now it can be easily shown, these are results which you are going to prove in assignments, that the identity of the group is unique. So it's not just there exists a identity, there exists a unique identity. But that's a result which I don't have to specify as part of the defining properties because it follows as a simple corollary from the defining properties. Similarly, the inverse of a given element is unique. A given element will not have two inverses. Again, a result which is very trivial to prove from the defining properties. However, another result which is not that easy to see directly is that these defining properties are actually not minimal, in the sense that I could have stated slightly less number of defining properties and still manage to define the group perfectly. One such situation is, I could just demand that there is a left identity, that is an E such that E star G is G for all G, and a left inverse for every element, that is for every element small g there is a G inverse such that G inverse star G is E. And the existence of the left identity and the left inverse is enough to guarantee the existence of the right identity and the right inverse. And not only that, also enough to guarantee that this right identity and the right inverse are the same as the left identity and the left inverses that we talked about. So I could have actually started out by defining or by reducing my defining demands on a group. However, the version of the defining properties that I've written down here are used most often simply because they are the ones which are most convenient to use. And one very important result, because the inverse exists for every element, there's a cancellation law, which means that if AB equals AC, where A is some given element of the group, because A inverse exists, I can hit this with A inverse on the left of both sides, and then I will immediately get B equal to C. Of course, if you think about it a bit, what we are really doing is we are applying the associative law as well. We are saying A inverse bracket open AB bracket closed. That's what I have on the left. But since I can put the bracket anywhere I want, this becomes open bracket A inverse A close bracket B. And A inverse A is identity, so E, B, that's B. And similarly, the right hand side becomes C. Just like you could cancel on the left, you could also cancel on the right. So if BA equals CA, this would imply B equals C. Notice on the other hand, A has to be either on the left, on both sides, or on the right on both sides. AB equal to CA does not guarantee that B equal to C, for the simple reason the CA and AC may very well not be equal. However, if the group is such that if for all G1, G2 belonging to capital G, G1, G2 is the same as G2, G1. So it does not matter which order you write the elements in. If you commute the two elements, switch their order, you get the same result. Then you say that the group is commutative or is abelian. That, of course, is named after the mathematician Abel. Since group multiplication does not commute in general, one result becomes very important. This is a result about the inverse of a product of two group elements. When you take the inverse of G1, G2, you actually get a composition of G1 inverse and G2 inverse, but you get it in the reverse order. So G1, G2's inverse is G2 inverse, G1 inverse. Now, it's very easy to prove this result. All you have to do is multiply G1, G2 by G2 inverse, G1 inverse, and check that you're getting the identity. Well, notice that we have taken G1, G2 here, and the brackets say, here the brackets are meant to indicate that you are multiplying G1, G2 first, and then multiplying the result by G2 inverse J1 inverse. However, you can use associativity to change the bracket and put it anywhere you want. In particular, you can put it here, and that immediately tells you that these two together will give you the identity, and hence you're going to end up with G1 inverse, which is of course the identity. So G1 G2's inverse is G2 inverse G1 inverse. Now there's a very easy way to understand why this inversion of order occurs. To invert something is basically to undo an operation. So when you do one operation after another, if you want to undo the overall thing, you have to undo the thing that you did at the end first, then you have to undo the thing you did at the beginning. Think about it a bit. There are plenty of examples from daily life which will convince you that this is the way it should happen. Of course, for abelian groups where G1 G2 is equal to G2 G1, this distinction doesn't really matter, because G2 inverse G1 inverse and G1 inverse G2 inverse will be the same for abelian groups. But since groups are non-abelian in general, you have to be careful about this one very important result. And one more important point must be stressed at this stage, and this is more about language than anything else. We will often abuse language and refer to the set G, which is the underlying set of a group, as the group G. So we will often use language like subset of a group G, whereas what we really mean is subset of an underlying set of the group G. Let me stress once again that the group is really defined using both the set and the product operation. But if the product operation is obvious from the context, we very often do not mention it and we use this language. In this lecture, we have taken a look at the basic structure of a group, its definition, some of the basic properties. We have also seen one example, which is going to be pretty important in whatever we are going to do next. In the next lecture, we are going to take a look at some more examples and some basic results which follow from these definitions.